Okay, in today's class we are going to study about BCD numbers, and we will see how to explore the ways by which we can use the 8051 to access individual bits of any particular port or RAM. Okay, let me first. Okay, now this is an important feature because even in 8085 this particular feature is there. That means how to handle BCD numbers in microprocessors or microcontrollers. Let me have the pen. Okay. So BCD numbers, we all know that BCD number ranges from 0 to 9, right? So BCD numbers can be represented between 0 to 9. Okay. If you talk about hexadecimal numbers, they can be represented from 0 to F, which you can call 15. And if you say binary numbers, then there are only two numbers which represents binary number, that is 0 and 1. So BCD numbers are very common in day-to-day life. Okay, so most of the people actually handle with BCD numbers itself, and microprocessors, microcontrollers, or embedded system, they work with hexadecimal numbers. But now the question is, how can we bridge the gap between the confusion of BCD and decimal numbers? How can the microprocessor understand whether the number is BCD or not, or what kind of operation should he do with the hexadecimal numbers to convert it back to BCD number? BCD numbers are, because BCD numbers are very commonly used in day-to-day life. That's why there is a focus always on every embedded system to to, to provide some facility so that the user can use BCD notations or BCD numbers itself. Okay. For example, we know that in BCD number, if we want to write 10, then it is 10. Okay. In BCD. But in case of hexadecimal, the same 10 is represented by A. Now, for a normal person, A is different from 10. But in hexadecimal, we know, because engineers know that A is 10 in hexadecimal. So we represent it like this. Okay. Now the question is, how the microprocessor actually handles BCD number? There are two types of BCD numbers. Basically, one is unpacked BCD numbers, unpacked, and the other one is packed BCD numbers. Okay, we know that to represent any BCD number, we need at least 4 bits. For that, 4 bits, because for example, if I write 0, 0, 0, 0, then it will be representing 0. Okay, and for any other number between 0 to 9, okay, we can use 4 bits to represent those BCD numbers. So what is unpacked BCD and what is packed BCD? Okay, now we know that in 8051 or 8085 or 8-bit number systems, they uses 8-bit to represent any number, be it 1, 2, 3, 4, any number, they uses 8 bits to represent that number. When we say unpacked BCD numbers, then in that case, the 4 upper bits will be always 0. Okay, the lower 4 bits will represent the number. Okay, so if I say okay, lower 4 bits, okay, will represent the number itself. For example, if you say 0, 0, 0, 0, 0, 1, 0, 1, then this is an example of unpacked BCD. Okay, unpacked BCD, because the upper 4 bits are always 0, whereas the lower 4 bits are representing the number. Similarly, if you want any other number, you can write those number between 0 to 9 representing upper bits only by 0 and lower bits, lower 4 bits or lower nibble by the number's magnitude itself. Then in that case, we will call it unpacked BCD. Now, what is packed BCD? In packed BCD, we use all 8 bits to represent that same number. Okay. For example, if we want to write 55, in that case, the number will be 01015. Okay. Then again 0101. So now this is a packed BCD because you are using all 8 bits to represent the number. So remember, this is the basic difference between packed and unpacked BCD. In unpacked BCD, upper 4 bits are not used, or you can say they are always 0, and rest of the lower 4 bits are used to represent the number. Whereas in packed BCD, we use all 8 bits to represent the number. Okay. For example, in BCD number, we know that, okay, this is important. 8051 takes 1 byte of memory to store store. Okay, store the packed BCD numbers. So packed BCD number, when we are saying, whenever you see packed BCD number, remember it is talking about all 8 bits being used. Okay. For example, 00 to 99. Now the question is how the microprocessor or the microcontroller can convert a number from one value to another value. If I say 80H, okay, this is hexadecimal value also. At the same time, I can go and say 80 decimal number. Okay, simple example. For example, if I say 10 in hexadecimal, then in that case, this number is representing 16 in decimal. Okay, whereas if I say 10 in normal language, then it is 10 in 10 in decimal also. So this is 10 in normal day-to-day life, but this is 16. Okay. So how the microprocessor actually converts one BCD number to its equivalent hexadecimal or hexadecimal number to its equivalent BCD number, because that's very important. So remember this particular line. Okay, remember this particular line. Whenever we want to convert any particular hexadecimal number to its equivalent BCD number, then remember, if it is greater than 9, if any number is greater than 9, like A, B, C, D, E, F, those are greater than 9. Okay, for example, decimal, we have 0 to 9 in decimal. Okay, in hexadecimal, we have 0 to 9, which is similar to that of BCD number. But after that, we have A to F. Now, because these numbers are greater than 9, these numbers have to be converted to its BCD equivalent. So now the question is how to convert these particular numbers to its equivalent BCD. So always add, okay, to correct this, the programmer should always add 6 to the number which is greater than 9. Simple as that. So if you have any number which is greater than 9, add 6 to that number and it will give you the BCD equivalent. Now, can the microcontroller do the same thing without any, that means the programmer then in that case have to add 6 to all the numbers whenever he sees A or B. So in that case, he will have to write a program which will be handling only adding 6 or not, or adding 6 or not. So he will have to write a program in which he will have to make that condition. If that number is greater than 9, then add 6 to that. So is there any alternative way by which the user can directly use some features of the microcontroller to convert a number to its equivalent BCD number? For that, there is an instruction called DA, decimal adjust. Okay. In 8085 we had DAA, I believe. Okay, let me check. DAA, or yeah, DAA, I think. So decimal adjust, it will, okay, DAA, decimal adjust accumulator. Okay, so in 8085 we have the same feature which is called decimal adjust accumulator. Okay, whereas in this is in 8051. In 8085 we have similar command which is called DAA. Okay, so this particular feature is available in almost all the microcontrollers or microprocessors. Now DA, this particular instruction allows you to convert a particular number to its equivalent BCD number. So it automatically adds the number 6 to that number and converts it into BCD. So you don't have to make a special condition that okay, you have to add a number 6 to all the numbers. For example, let us look at a simple example. Here we are adding two numbers which are hexadecimal in nature. Okay, just a second. Okay, now here you see accumulator is getting 47, which is hexadecimal. Then we are adding 25, which is again hexadecimal, and we are adding accumulator with B. That means these two numbers are getting added, and then at the end we are going to adjust the decimal. We are passing the command decimal adjust. Let us see what this particular program is going to do. So in accumulator you see we have 47. Now in B we have 25, and we are going to add these two numbers, and it is going to give you 6C. Now the question is, after the addition we got a number. After the addition we got a number 6C. 6C. So out of these two numbers, only C is the number which is greater than 9. Right? So when I pass this command decimal adjust, he will only decimal adjust this particular number for you. That means he will add 6 to that particular number, and he will give you the actual value of the number in BCD. Let us see what does that mean. It is not going to add plus 6 with this. Okay, remember, he will add only plus 6 with this. Plus 6 will not be added in this number. Okay, now right now in the accumulator we have 6C. Now I am going to decimal adjust the accumulator. So the content of accumulator is going to be decimally adjusted. So now you see 72 is the answer. So C was added with 6, and you got, okay, C was added with 6. Wait a second. And you got 72. So the equivalent decimal number for this particular 6C is 72. It automatically converted that for you. Okay, so now in this way the user don't have to worry. Now remember, this number is not hexadecimal, this is decimal number. Okay, so now the content of accumulator is purely decimal. Before it was hexadecimal, so he automatically converted this particular command automatically converted your number to decimal number itself. Similarly, if we take a separate example in which both the numbers are hexadecimal, assume, okay, let me clear this program. If both the numbers are hexadecimal, okay, I am going to put accumulator 77, B is 55, going to add them. Now you see both are CC. Okay, so that means now we have a number which is CC. Okay, I'm not getting the pen. Now we in the accumulator we have CC. So that means now the decimal adjust will add plus 6 to both the numbers to get its equivalent total number. That means he will generate a number which will represent the decimal value of the total number CC. So let us see that. Okay, so now you see the accumulator has got 32. Okay, but remember the status of the PSW also. PSW shows there is a carry generated. Okay, so there is a carry generated. So 32 is not the complete answer. Remember that thing, because there is a carry generated. So we got, after conversion, we got 32. Okay, in the accumulator. This is in the accumulator. But at the same time, there is 1 in the carry. So the answer is 132. So now the programmer can use this particular command to convert hexadecimal numbers to its equivalent decimal number by using DA instruction. Okay, so this is one of the good features of any particular microcontroller, that there will be a command which will automatically convert the hexadecimal numbers to its equivalent decimal number, and you can use them to understand what is the actual number in your real life. For example, we generally don't deal with CC and all these things. We generally work with 132. So if you need to read the number as 132, okay, 132, in that case you just have to pass a command DA. Okay, so wherever you need to convert a number to its equivalent decimal, remember, use DA command. Now coming to unsigned multiplication and divisions. So 8085, okay, 8085 do not have any instructions, do not have instructions instruction to multiply or divide numbers. Okay, remember, so this is one of the so-called, we can say, drawback in 8085. But we can use loop by which we can add the number x number of times to get the summation of the, or we to get the multiplication of two numbers. But in 8051 we have dedicated instructions to multiply two numbers. For example, you can use MUL instruction to multiply two numbers. But the thing that you have to remember is that upper byte of the result is stored in B register, okay, not in accumulator. So upper byte will be stored in B register, and lower byte, okay, byte will be stored in accumulator. Okay, so after any multiplication, the result, when we are saying how can we read the result, then you have to read both accumulator and B register, and in the B register you will get the upper byte and the lower byte will be in the accumulator. Remember this thing, because sometimes people get confused that accumulator will get the upper byte and lower byte will go to the B register. So don't make that mistake. Let us try a simple program. Okay, so we have in A 09, in B we have 04, and after multiplication, okay, after multiplication accumulator got some number and B got some number. So wait a second, reset, go and put an end. Okay, so 9 into 4, if I go to the calculator and take the hexadecimal value. 9 into 4 is not 36 because we are multiplying two hexadecimal numbers. So I am working with hexadecimal numbers. 9 sorry into 4, right? So you got hexadecimal value 24 in the result. Okay, therefore the answer is actually 0024. Okay, the result of this multiplication 9 into 4 is 9 hexadecimal multiplied by 4 hexadecimal is 24 hexadecimal. But remember 24 is 8 bytes only. Okay, so the actual number is 008 bytes and then 24. So 24 goes to accumulator and 00 goes to B register. So if this multiplication would have generated a larger number which will occupy almost 16 bits, okay, then in that case we will get the any number other than 00 here. Okay, so let us try and multiply a bigger number so that we can see what is the content of accumulator and B. Remember 24 is the answer, but 24 is written in 16 bits, so 0024. So upper byte is 00, lower byte is 24. So 24 went to A and 00 was uploaded in B. Now in this example we are going to multiply two numbers 25 and 35. Okay, I am going to multiply 25 with 35. Now you see the number result is 7A9. So 35 hexadecimal multiplied by 25 hexadecimal is going to give you 7A9, right? Yeah. So 7A9 again you have one particular nibble still 0. Okay, so remember A9 will go to accumulator and 07 will go to B register. Okay, let us try and check. Okay, I will just modify the program. Reset. So 35 is in the accumulator, 25 is in B register, and when we multiply we got 07 in the B register and A9 in the accumulator. Okay, so lower byte is in the accumulator and B got the upper byte. So remember when you read, you should read 07A9, not A907. Okay, remember this thing, you should not read A907. This will be wrong. Okay, this particular number is correct, 07A9. Now coming to the next instruction, which is division. So how can we divide two numbers in 80851? By using the command div. So div command divides two numbers. Okay, remember the quotient is stored in the accumulator and the remainder is stored in the B register. So B register and accumulator. So B register gets the remainder. Okay, and accumulator gets the quotient. Okay, so let us try. For example, A is loaded with 95H divided by 10H. So definitely you are going to get remainder and quotient. So the quotient will be 9. Okay. And remainder will be 0, 5. So this will be loaded in accumulator and the remainder 0, 5 will be loaded in the B register. Let us check. Okay. So, sorry. You see here B got 0, 5 which is the remainder and accumulator got 0, 9 which is the quotient. Done. So this is multiplication and division. Now coming to one important flag which I said okay we will discuss later. That flag is overflow flag. Okay. Overflow flag is different from the carry flag. Carry and overflow, they both look like okay they are almost similar, but no, they are different, because carry flag is generated only when any number is overflowed from d7th bit to the carry itself. Okay, so if there is any number which is generated or which overflows from d7, in that case carry flag will be generated, whereas overflow flag, okay wait, something has mixed here. Okay, now carry flag will be generated only when a number overflows from d7 to any upper bit, whereas overflow flag has its own different condition. So overflow flag can be set under two different conditions. One is when there is a carry from d6 to d7. Remember, there is a carry from d6 to d7 but no carry from d7. That means suppose after the addition a number was generated from d6 to d7. Okay, a carry was generated from d6 to d7 but no carry was generated from d7 to any other number. Let us take an example. 0 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0. So if I add these two numbers, definitely there will be a carry generated from d6 to d7. Okay, so this will become 0 0 0 0 0 0 0. But this carry is limited to d7 itself, so the answer is 1 0 0 0 0 0 0. But now you see there is no carry from d7 onwards, so definitely this condition or this summation is going to generate overflow flag and it will set the overflow flag. So this is the first condition, that carry should be generated from d6 to d7 but no carry from d7 to higher bit. Okay, this is the first condition. Second condition, there is a carry from d7 but no carry from d6 to d7. So just change this number. Second condition we can check like this. For second condition we have a number something like this. Okay, where now there is no carry from d7 6 to d7. Okay, no carry is generated from d6 to d7, but there is a carry which will generate from d7 to higher bit, so it will become 0. So the accumulator will contain 0 and carry flag will be 1. Okay, in this case overflow flag still will be 1. So now remember these two conditions are important. So when you look at overflow flag, you must remember that you should look at d7 and d6 both. Okay, but the overflow can generate from any either of these two. It will not be generated, it should not be generated from both. Okay, only from either D6 to D7 or D7 to any other upper bit, okay, but not both simultaneously. Okay, what does that mean? So any addition which may look like this, for example 1 1 1 1, in this case what is going to happen, there is a carry from D6, okay, so there is a carry generated from D6 to D7. At the same time there will be a carry from D7 to D, um, okay, not D7 to any upper bit. In that case this overflow will be reset, it will not set, okay. So remember, either one of these two conditions should be true, not the two simultaneously, okay. This thing has to be kept in mind. Now, okay, let us take an example. Now in this example there is something important to see here. In this example we are using both the numbers which are in decimal format. Both the numbers are in decimal. Remember, here we are not putting any h after the number. So since there is no h after the number, this number is simply decimal number. So now the question is, I have minus 128 which will go to the accumulator, okay, and then I have minus 2 which will go to the register R1, and then I am going to add these two numbers. That means minus 128 minus 2. What will be the result? But before that, keep in mind how this microprocessor or microcontroller store this number. Okay. So when we say, okay, okay, when we say, for example, minus 2. So the microcontroller is not going to take this minus 2 in just minus 2 itself. So he will take this particular number in some particular format that is called 2's complement format. Okay, 2's complement format. For that, he will take this number. Okay, so this number is 0 0 0 0 0 0 1 0. Then after that, he will take 1's complement 1 1 1 1 1 1 0 1, and then add 1 to this number. Okay, so that you will get the 2's complement. Okay, so this is the number which is going to be stored in the accumulator. So accumulator will get f, I think this is e, fe. Okay, so minus 2 will be stored as fe in the accumulator, and similarly 128 will be converted to its equivalent 2's complement and will be stored to, no, this is fe is going to not accumulator, but here in the program it is going to R1. Okay, so similarly the 2's complement of 128 minus 128 will go to the accumulator, and then we are going to add these two numbers and we are going to check what will happen to the overflow flag. Okay, so let me try if I can generate minus 128. So I am working with hexadecimal number. I'll clear it, 128. Okay, I will try minus. So FED8, I think FED8 will be stored in no, not hexadecimal, sorry, because the number is decimal here. So I will take 128, okay, and minus. So FF80 should be there in the accumulator. Let's check. So okay, assemble. So in accumulator we have 80 only. Okay, so 80 is representing minus 128. Okay, and then in B we have, no, in R1 we have FE, which is equivalent to minus 2. So 80 and FE. Let us write these numbers. So we have 80, which is okay, and FE. So these two numbers are going to be added. So remember here, after the addition, this will be 1110. Okay, it is simple 111. But there is no carry generated from D6 to D7. There is no carry. But remember, after this addition, there will be a carry generated from D7 to higher bit. So it will become 0, and there will be a carry generated at this after this addition. So that means the result will be 77E. Okay, but remember there is a carry also, so 17E. Anyway, so now the question is, will the overflow flag be affected or not? Yes, the overflow flag will be affected because there is no carry from D6 to D7, but there is a carry from D7 to higher bit. Let's check. Right now you see only parity flag is affected. Now I am going to add these two numbers. What happened? Wait a second.
सर ऐड ए कॉमा आर फोर कर दिया कल.
Okay, sorry. Okay, okay. Let us try. Now there is a carry which is generated. Yes, carry was generated. At the same time, you have overflow also generated. So you see overflow is generated because there was a carry generated from D7 to upper bit, but there was no carry from D6 to D7. Therefore, overflow is generated. At the same time, carry is also generated. So remember, it is not that these two will not be set simultaneously. They can be set simultaneously. Only thing you have to remember is the overflow flag is generated only when one of these two conditions are met, not both of them. Okay. Okay. Let us try this program. Sorry, controller. So in the accumulator we are sending 7. In the R1 we are sending 18. But the 18 is 12 in hexadecimal. Remember, these two numbers are decimal because there is no H after these two numbers. Okay. So these two numbers are simple decimal numbers. So in the register R1 we have 12. In the accumulator we have 7. And when we are going to add these two numbers, okay, check the status of the carry is 0, overflow is 0, only parity is 1. Okay, we added this. Again, what happened? Something. Okay, let me check if there will be carry or not, because yeah, that condition might not be true. Okay, for example, here we have 7 and 18, which is 12. So 7 is going to be written like 0 0 0 0 0 0 1 1 1. Okay, done. And 18, which is 12, 12 means 0 0 0 1 2. So 0 0 1 0. Okay, if I add these two numbers, okay, there is no carry from D7 or no carry from, because it is simple. We can see that this is 1 0 0 1. 1 0 0 0. Okay, there is no carry from D6, neither there is any carry from D7. So definitely the overflow is not affected. Okay, now coming to some so-called important things regarding the programming. Okay, we know that there is AND operation in 8085, and this AND operation is available with the 8051 also. Generally, we always keep in mind that okay, AND will be ANDing the bits, for example, like this. If I'm going to AND 1010 and 1010, and if I suppose AND this number with 0101 0101. Okay, so when we say ANDing, then these are bitwise ANDing. Remember, bitwise ANDing. So bitwise ANDing means bit to bit there will be ANDing operation. So 1 cross 0 0, 1 cross 0 0, 1 cross 0 0, 0 0 0 0 0. Okay, so the result is 0. This is clear. So we always think that okay, ANDing operation is helpful for this purpose only, that when you multiply two numbers, if there is a 1 and a 0, it will become 0. If both the bits are 1, then only the result will be 1. Clear, that's true. But generally these operations are used for masking certain bits. This is the most important thing. We do not look, sorry, we do not look into ANDing operation from this perspective. This is important. We actually can use ANDing operation to mask certain bits. Mask means we can forcefully make them 0. Okay, we can forcefully make them 0 after, for example, if any bit is 0 or not, I can forcefully make that particular bit 0 by using AND operation. So you can remember it like this. Uh, we can make bits 0 by AND operation. So this is important. Okay, so you can use AND operation to make a certain bit or a certain bits 0. So this is important, 0, making 0. Okay, so this is masking in this case. For example, for example, okay, now suppose I want to make this particular bit 0. Okay, I want to make this particular bit 0, only this particular bit 0. Okay, in that case what I can do is I can multiply this with 1111. Okay, 1 1 0, because I want to make it 0, and 1. So what will happen? Wherever the zeros are there in that previous number will remain there. It will not be affected. Wherever the ones are there, they will also remain there. Only that particular bit which I intentionally want to make 0 will become 0. For example, 1 cross 0 is 0. Even the number also had 0. 1 cross 0. Now I am forcefully making that 1 0. Previously it was 1. Now I made it 0. Now rest of the numbers will remain same. It is not going to affect any number or any bit other than the bit which I intentionally made 0. You see here, these two numbers are almost same except this particular bit. Similarly, I can force any other bit also or more number of bits also to make 0. So that means I can forcefully make bits 0 by using AND operation, and we call it masking. So to mask any particular bit, we can use AND operation, and we can make a certain bit or more number of bits 0. Okay. Okay, just for example, 35 and F0F. So 35 means 0011. 5 means 0101. Okay, and I forcefully can make it 0. Okay, 1111. Clear? So now here you see rest of the bits will remain same. Only those bits which I forcefully want to make 0 will remain there. So I am forcefully trying to change these two bits. Rest of the bits will remain there itself because I am multiplying with f. So 1 cross 1 1, previously there was 1. 1 cross 0 0, previously also there was 0. 1 cross 1 1, 1 cross 0 0. So all these bits remained intact. We didn't change the bit position or bits value. Now here in this case, when we are going to forcefully make it 0, you see two of the bits were made 0 forcefully by ANDing operation. So remember, ANDing operation makes the bit or certain bits 0. And this is sometimes very important. For example, when you want to make a certain LED forcefully off after any operation, then in that case you can use this kind of operations, ANDing operation. Okay, clear. Now coming to OR operation. Similar to that, or and we have OR operation, which we believe that whenever we do OR operation there will be bitwise ORing. Clear, no issues. But generally OR operation is not commonly used for just ORing some bits or so. These are used again for making certain bits 1 or to set certain bits. Okay, this is important. So OR operation is used to set certain bits of the operand. Okay, so if you want to make certain bits high, just like and we made certain bits 0, we can make certain bits high by using OR operation. Okay, simply for example this program. So 0 0 0 0 5 0 1 0 1. Okay, 5, and I am going to OR with 5 0. So 5 means 0 1 0 1 0 0 0 0. Okay, here what we are doing, we are ORing with, that means here we ANDed with 0. So in AND operation 0 was important, remember. Okay, 0 was important in AND operation. In OR operation 1 is important because wherever you want to make that particular bit 1, be it 1 from the last state or whether I don't care. For example, if forcefully I want to make this particular bit 1, so if that number is 0 0 0 0 0 1 0 1, I forcefully want to check whether this number is 1 or not, or if it is not, I want to make it 1. In that case, remember, I will add certain number which will have 1 in the least significant bit. Okay, so if I add this number, whether this number was 0 or 1, it does not matter. After this addition, this number will become 1 for sure. Okay, whether it was 0 or 1, it does not matter. Okay, this number was 0 or 1, does not matter. I am just going to make it 1 forcefully. Okay, so this is the operation for ORing. So now here in this case, we are forcefully making these two bits, this one and this one, 1. Okay, so wherever you want to forcefully make it 1, bring 1 to that positions. Okay, so now the number will be, so 55. Okay, so this is how you use the OR and operation. Remember, and makes 0. For that you use 0. Or is used to make 1. So or is used to set bits, and we use 1 in this operation. Okay, so or comes with 1 and comes with 0. Okay, so to set a number use or, to reset a number use and. Okay, done. Now there is another operation called XOR. You must be very, you must be thinking that almost all the microprocessors starting from 8085 itself, okay, they provide you this particular operation. So the designers found that XOR is very important. Why they didn't come up with the NAND or those kind of operations? So before that, they introduced XOR. There is no command for NANDing or NORing a certain number, but the designers came up with XOR command. So definitely XOR command has got some very important features. So XOR command, for that you have to use XRL instruction. Okay, to perform XOR operation, you use XRL command. Okay, but remember, XOR operation is handy when you want to check whether, okay, when you want to check whether two numbers or two registers or two values are same or not. So for example, if you want to compare two registers R1 and R2, and you want to check whether these two numbers have the same number values or they have different values, for that condition you use XOR operation. It is not just for XORing. It is to check whether two values or two numbers are same or not. The same thing is used mostly in VLSI also, XORing, to check whether two numbers are same or not. The same thing is used in communication also. Okay, communication, to check whether the transmitted signal and the received signal are same or not. So this is the way XOR is very important. Okay, this is why XOR is very important. For example, when we XOR two numbers which are same, remember, if two numbers or two registers have same value, if they have same value, then after XORing you will get 0. This is one of the most important feature. So if two registers have same value and if you XOR them, you will get 0 in the accumulator. So by looking at the 0, you can say that these two registers had same numbers. Okay, otherwise it will not give you 0. Okay, let us just see a simple program. This one. Okay, so both these numbers have 55 in accumulator, and I am going to, okay, I am going to put 55 into accumulator. So accumulator have 55 and we are XORing the content of accumulator with 55 itself. So if these two numbers are same, then the result in accumulator should become 0. Clear? We have 0 in the accumulator. So XORing makes the, if two numbers are same, the result will be 0. By that we can check whether the two numbers were same or not. A kind of comparison. Now coming to some important features, single bit instructions. Single bit instructions means those instructions which work only on a bit, not on the whole 8 bits. Okay, which you can use to specifically operate on a particular bit. So those instructions are set bit. You can set a particular bit, clear bit, complement the bit. So if the bit is 0, make it 1. If it is 1, make it 0. Okay, so complementing, make it 0 to 1 or 1 to 0. Jump if the bit is high, which you have used yesterday to display, to check whether the switch is on or off. Okay, so, or you can use jump if the bit is not high. Okay, so these two operations are very handy when you want to check whether some switches are on or off, or okay, you can check that. And third one is jump bit. If the bit is high, jump to certain target, but before jumping, clear that bit also. For example, suppose P1.2 was high. Okay, was high. Initially it was high. And I want to check whether this particular, this, suppose here we have a switch connected to this port. Okay, and this port is right now high. That means the switch is getting 0 value, because in the simulator we found that we had VCC And if the switch is pressed, that VCC goes to ground. Otherwise, by default, the port is connected to high. Okay. Otherwise, let us take it simple example. Here we have this particular connection. Okay. Here you have ground. So that means by default, the port is 0. When the switch is pressed, the port gets 1 or high. So suppose the port is, the switch is closed. In that case, the port is getting 1. Now, when this particular switch is pressed, the port gets 1. Now I want to check whether the port is 1. If it is 1, make some other port or make an alarm on or some other task to be done. In that case, what you can do, you can use this instruction also. Jump the bit if the bit is high. Yeah, if the bit is high, go to a subroutine for alarm. Okay, jump to that particular subroutine, but before jumping, make this particular number 0. Okay, so that otherwise what will happen, this will keep on going back and forth and making the alarm high. So before jumping, make this particular bit 0. Okay, so this is the operation for JBC. So you can use JB, JNB and JBC if you want to use or check certain bits are high or not. Now for that, you can use this port 3, port 2, port 1 and port 0. Addresses of port B, port 3 to port 0. How can we get these addresses? How can we get these addresses? These addresses are present in the SFR. If you remember, we discussed about the special function registers. So you see here port 0, port 1, port 2 and port 3. And how can you remember that? Port 0 starts from 80. And remember, all these SFRs are ranging from 80 to FF. So the location 80 to FF is restricted. Okay, we shall not be using these locations, which are vacant also. So special function registers ranges from 80 to FF. And then you check port 0 plus 10, you will get port 1. Plus 10, you will get port 2. Plus 10, you will get port 3. So if you remember that port 0 is at 80, then you just have to add 10, 10, 10 and you will reach to port 3. Okay. So these are the locations of port 0, 1, 2, 3. Now, so that means B0 is the address of port 3. So B0 is port 3.0. B1 is port 3.1. B2 is port 3.2. Similarly, B7 is port 3.7. Okay, similarly, port 0 is 80. So that means 80 is representing this particular bit, port 0.0. Okay, similarly, port 0.7 is 8787. Okay. Okay, now let us see how we can use these two conditions, that means single bit instructions and the addresses of the port, to check whether a particular switch is pressed or not. And if it is pressed, then we have to make certain LED high or not. Okay, so let us check this program, what this program is going to do. So in this, by this program, simple program, we can check whether this particular bit is high or not, whether that particular switch is high or not. If it is high, then you can make some conditions and then you can go back. Okay, now the question is, first, port 2 is loaded with 0FF. What is the purpose of loading port 2 with 0FF? Why we are loading port 2 with 0FF or FFH? Why we are loading?
To make it an input port.
So now this becomes an input port. So port 2 is going to act as an input port. Okay, and of course we are using the port 1 also. So definitely port 1 dot 0 is working as output port. Now the question is why we are doing this thing, why we are choosing port 2 be an input port and port 1 to be an output port. For that you can go and check the schematic. Here you can see, here you can see port 1 is connected with LEDs. Okay, so port 1 will provide you the output. You can see the port 1 is connected with LEDs, so port 1 is going to provide you output, whereas port 2, if you see here, port 2 port 2 is connected to switches, and definitely switches are going to act as input port. So this is why we have used port 2 and port 1. Okay, and port 2 here is acting as an input port. So initially we initiated the port 2 with FF, that made the port 2 input port. Now what we are going to do, assemble. Okay, now look at here, these are the LEDs where we will get the output. Okay, and these are the switches which will correspond to the input, and we will check them bitwise. So set bit p 1.0. So set bit p 1.0. Why setting the bit didn't make it high? Why the LED is not on in this case? We set port 1.0, but still the LED is not on, because you see here port 1.0, if I set it, set means making it high. If I make it high, this particular pin is connected to the LEDs N, and the P of LED is plus 5. So both P and N are at high voltage. So definitely LED 0 will be off. So by default, we started with the program and we said, okay, make the LED at port 1.0 low. Then after that, we are saying jump if bit 2.0 is activated. Okay, if it is high, remain here. So let us check. So that means right now the pin is high. Why the pin is high? If you check the schematic, port 2 by default is connected to plus VCC. See here, port 2 is connected to plus VCC by default. When the switch is pressed, this port becomes 0. Okay, that means it becomes low. So jump if bit is high. Yes, bit is by default high, so it will remain in that particular position. Clear? So the loop is just rotating here itself. Now what we are going to do, we will make the port 2.0 low. So now when I press the switch, now that switch is connected to ground, so it became 0. Now I will come out of that loop. You see, I came out of that loop. And then we are saying clear CLR. Again, it is a bitwise instruction. So clear port 1.0. We are making that port 0. So what will happen? Now the port P is connected to plus 5 volt, and I am making port 1.0 low. So now here you have high voltage, here you have low voltage. The LED will blink, or it will get on, not blink. Okay, now you see the LED is on. So the switch is, when the switch is pressed, that means when the switch is grounded, the LED became high. And jump if the port 2.0 is not high. Okay, so it will remain in this particular loop itself. So until unless the switch is again released, or it gets high voltage, it will keep the LED high. So let us run the program. Now we understood the program. So the program is running in the loop, and when I release the button, or when the switch is off, then the LED is off. When I press, the LED is on. So this is how we can use bitwise operations to make simple switch based operations or LED to become high. Now, simple program, but it is very useful, because it is not that you just can use the switch. Here you can use sensors, analog sensors also, by that you can compare some number. If that number has reached to certain threshold, you can make the port or any particular alarm high depending on your choice. Now coming to some very important features that are called bit addressable RAM. When we say RAM, remember RAM ranges from 00 to 7F. No, FF. I think, wait a second. 7F. Okay. It ranges from 00 to 7FH. So now the question is, in this range, what are the things that we can keep in mind? So remember, there are banks in this particular range where we have bank 0, 1, 2, 3. We know this thing. Bank 0, bank 1, bank 2, and bank 3. All these three are there in this particular range. So what is the address? It is address is 002 07. Then bank 1 08 to 0F and so on. Okay, 10 to 17 and 18 to 1F. These are the banks, and by default this is the bank which is used for because these banks are always R0 to R7, and this is the by default bank which is used for temporary registers by the 8051 default bank. Okay, and this is the bank which is used by the microcontroller for stack. And remember, you can change the stack, change the address of the stack just by initiating the stack with some other number. Just say, okay, move some address into SP. Okay, so move SP comma some address. It will change the stack's position. So we know about this thing. So that means all the banks have finished by reaching 1F. 1F is the last. So that means 0 0, okay, 0 0 0 0 to 1F. Clear? We have finished the banks. Now if I go above 1F, after 1F we will reach to 2 0. Okay, you can check it from here also. Okay, after 1F, this is 1F, here you have 1F. Then after that the next address is 20. So there is something important to remember in this thing, that from 20 to 2F, remember 20 to 2F can be accessed bitwise, can be accessed bitwise. So address 20 to 2F can be accessed bitwise. That means you can access a single bit of this particular address. Okay, though they are all 8 bits. Okay, if you take this particular 2F, it is 8 bit. Okay, but still you can individually use a particular bit of this particular location of the RAM. So this is called bitwise addressable RAM, which is 20 to 2F. So definitely 20 is 00. Okay, 20 starts from 20. Okay, starts from 00. Then after that, so that means 20 has got 8 bits. Remember, this particular register has got 8 bits. Okay, so you can access individual 8 bits from by using 00, 01, 02, 03, 04, 05, 06, 07. So this is the address for all the individual bits of 20. Then to access the individual bits of 21, you can go from 0820F. Similarly, you can increment the addresses, and remember, when you reach 2F, 78 to 7F are the addresses for 2F. So this might be a bit confusing for you, but try to understand this thing, that address ranges from 20 to 2F can be accessed even bitwise. That means you can access an individual bit of that particular. For example, if you want to access R0's particular bit, we know that R0, okay, R0 is 8-bit register, right? So 8-bit, if it is 8-bit register, can I access R0.3 or R0.5? Can I access them, or can I make them high or low bitwise? No, you cannot access bitwise. Okay, is not allowed. Why? Because that does not fall in the bitwise addressable location. So similarly for R0, R1, R2, R3, R4, R7, whether you go for any other individual bits between any other bank, okay, you cannot access them bitwise. So bitwise access is not allowed. Okay, not allowed. Okay, not allowed. So which are the memory locations in the RAM which can be accessed bitwise? These locations from 20 to 2F. And what are the addresses of individual bits? For 20, the individual bits start from 00, 01, 02, 03, 04, 05, 06, 7. Similarly, you can go on incrementing the addresses up to 7F. So now here there are two confusions. This 7F, okay, and this 7F. These two are two different 7F. What does that mean? This 7F is the location within 2F, which is bit addressable. And some instructions can access this particular 7F by using bit addressable commands. Whereas this 7F is the register itself. Okay. Here this 7F is within 2F, whereas 7F has its own register, 8-bit register. So remember that there is a location within the RAM which can be accessed bitwise, and that range is from 20 to 2F, and we can access them by noting their addresses itself, like 000107. For example, now how can one use these particular addresses? For that, for example, if I just write if I write set bit 42, okay, if I'm saying set the bit 42 only, then in that case what will happen? Because 42 is not a register, okay, and neither it is a memory location directly. So what it will do, it will go to 42, which is here, okay, and individually you can set that particular bit. So 42 is in 28, and 42, this bit will be high because you are setting that particular bit. And how can we see that in the software? Okay, let us take this program, reset. Okay, so this is just a simple program. Now remember, you have to keep an eye on the data memory. So okay, data memory has got some garbage value. I will close this program so that there is no garbage value in the data memory. Okay. Okay, so now you can see all the bits or all the registers in the data memory 00 to 7F are 0. Now when I pass this command set 42H, so I told you the location 20 to 2f are bit addressable. So this is the line, or this is the memory which can be accessed bitwise. Okay, so 20 to 2f. So within this bit 28, so where is 28? 20, 21, 22, 23, 24, 25, 26, 27, 28. Here in this is an 8-bit register. Out of these 8 bits, I am going to make one of the bits high by passing the command set bit 48. Let us check. Keep an eye here. Okay, this particular location 28. Okay, assemble step. Okay, see here at the location 28 we got 04 04. Okay, so if I write that particular number in hexadecimal, in binary, so what I'm going to get? I'm going to get, okay, I'm going to get what I did, I got 04. So 0000400100. So this is the address of 28. Okay, 28.0, 28.12. So let us check what is that address. Here you see 42. So if I make this particular number 0 0 0 0 and then 0 1 1, okay, then 0 and 0. So now if you read this number 0000 is 0, 0100 become 4. So in the 28 memory location 28 we got 0 4. Clear? So remember this line, that means 20 to 2f can be accessed individually bitwise, and we can set or clear any of these particular bits within the range from 20 to 2f by accessing their addresses. What are their addresses? For their addresses, remember, you start from 20, sorry, you start from 20, sorry, 20. So 20, first bit is 00, second bit is 01, 02, 03, and so on. You keep on incrementing this value until unless you get 7f, that is 2f. Okay, these are bit accessible. So if you say set bit 7f, set bit 7f, in that case this particular 7f is not going to be accessed. Remember, this 7f is different. This is a register, complete register, whereas this 7f is a bit only. So when you say set bit, if you say set bit 7f, in that case you will be enabling this particular bit only. Okay, you are pointing at this particular address. Remember, you are not pointing at this address, not pointing at this address. This is a bit more confusing, but if you practice, you just practice 10 or 15 times, you will remember this thing. Okay, okay, so now, okay, what is this? Write a program to save the status. Okay. Write a program to save the status of port 1.2 in bit location 06 and the status of port 1.3 in bit location 07. Okay, you can just write this program, no issues. Okay. Let me check whether this program is important or not. Write a program to save status of port 1.2 in bit location 06 and 1.3 in bit location 07. Port 1, why I am using port 1? This is output port, right? So I don't think there is need to write the values of output port in somewhere. Jump if bit is not 0 to port 1.2. I think there should be, we should go for port 2.3 and 2.1. Okay, just try that. Okay, it's your choice now. Now coming to another commands where you can use bitwise operations, single bitwise operations, especially with carry flag. Okay, so today we focused on only bitwise operations basically. So to carry flags, so you can use set bit carry. Forcefully you can make the carry high, or you can make it clear, complement it. You can take the bit carry bit to a particular bit location. Bit location, when we are saying bit location, okay, when we are saying bit location, then remember we must be pointing to a bits location only, because cy is only one bit. This is one bit. So if you are going to use a bitwise or bit location, then you should remember that you can use the previous memory range between 00 to 2f. Okay, 00 to 2f for the bitwise operation. Now similarly you can take a particular bit location and move it to carry also. For example, if you want to say, okay, take 7f, if you are just saying move c comma 7f, then that means this 7f is not a register, this is a bit which is in the memory location 202 to 28, 2f, 2f or 28. Wait a second, 2f, yeah, I'm tired. Okay, so 2f. Okay, so you are taking that particular value to the carry bit also. And then of course jump if there is no carry, jump if there is carry. We have used it in 8085 also. And then and the carry bit with the particular bit in the location, and then and carry, and this is important, slash bit. Okay, I have not used this command in the simulator, but this command is important. So and the carry with inverted bit. Remember, so if the bit is 0 in the memory location, invert it first and then AND it, and then save it on the carry bit itself. So invert it before. This is, for example, carry is ANDed with the bit, but here in this example or in this code, you invert the bit first and then AND with the carry. Similarly, you can use O or L, that is OR. So invert the bit first and then and or with the carry. So invert before, that is we can say invert bit before ORing. Okay, done. So this is about carry flags bitwise operation. There might be another bitwise so-called commands in 8051. We are not going into that because this is what I found very important to work with 8051 till for our labs purpose. I am teaching this part only for the lab purpose. This is not course itself. Okay, now briefly talking about the interrupts, though we will not be using the interrupts, but you can use the interrupts if you want. So if you want to study 8051 in more depth, you can go and study it. So definitely interrupt is one of the most important feature in any particular device, be it 8051, 8051 or any other microcontroller or microprocessor, because we cannot always depend on polling. Okay, polling is not the solution. Polling is not the solution. So polling is avoided mostly. Okay, pollings are mostly avoided. So what we do mostly, we will work with the interrupts. The more the interrupts a system will provide you, the better the system is. So, and of course interrupts will be coming with the priorities also. Okay, so there are basically 6 interrupts in 8085. Okay, and out of these 6 interrupts, basically there are only 5 interrupts, but we call them 6. Okay, one of the interrupt is reset. Reset is one of the interrupts, but reset is not considered to be interrupt in a way itself. Okay, so we can say we have reset, which is a kind of interrupt but not a pure interrupt. Okay, so reset, when you press this button or when you reset the microcontroller, then the microcontroller jumps to the location 000 H. So there is one circuit which we always have to make with the microcontroller, whether it is 8051 or any other microcontroller. So basic simple circuit will have a crystal. Okay, always will have a crystal that will be connected to x1 and x2. Then definitely we will have VCC. Okay, we will have VCC, this is very important. And then we will have the ground also. Done. But of course there will be always RST pin, reset pin, which can be either always kept high or should be always kept low. Okay, so crystal we generally use capacitors also. Capacitor going to ground, capacitor going to ground. Okay, but reset again, it is generally either kept in high or low depending on the behavior of the IC itself. Let me check. I believe in 8051 we have to keep this particular pin always low. When we provide high, this becomes reset. So we should not provide it high in any case. Let me check, just give me a second. Uh, okay, it is, I cannot see in the book right now. Okay, let me check in Google. So we call it mm, what circuit? Uh, Not the basic circuit. There is a name for that. Or let me check this particular circuit. Okay, here you see view image. You see here that this is the reset pin, pin number 9. Okay, by default it is connected to plus 5 volt and there is a capacitor. Okay, there is a capacitor connected between 5 volt and pin number 9, and then it is grounded with a 10 kilo ohm. So by default when the power is on, you see the capacitor becomes open circuit because you are connecting a DC voltage to that. So open circuit, by default it is open circuit. But when you press this switch, the moment you press this switch, the 5 volt reaches to pin number 9, and that means the microcontroller resets. So never control plus 5, connect plus 5 volt with the reset pin. But generally whenever you see a reset button is there, push to on kind of switch, because this is push to on. So if by default it will be always off. When you press this switch, 5 volt reaches to the pin number 9 and it resets the microcontroller. Otherwise, if the switch is off, this capacitor takes maybe some milliseconds to charge, and by after that it will be acting as an open circuit. When it is open circuit, this 5 volt can never reach to the pin number 9. Okay, until unless there is some very high AC signal in this part, plus 5 volt. Okay, we'll leave that part. So this capacitor is keeping the plus 5 volt away from pin number 9. When you press the switch, it becomes high. So this don't recall this particular name of this circuit. This is the most important circuit of any microcontroller. So remember, there will be always a crystal. You have to use crystal. There will be capacitors to clear out the noise from the crystal, which will be grounded. There will be a ground. There will be a VCC. So these are the most, this is the most basic circuit that you have to prepare before using the microcontroller or before using any port. Okay, pin number 31, this is VDD, I think, and it is again connected to plus 5 volt. So you have VCC, you have VPP, I think this number is VPP, and then you have ground, crystal, and the connection for reset. You have to make this basic circuit before working with any microcontroller. Okay, so what we are doing, we are using capacitor here, connected here, resistor going to ground, and then there will be a switch. which is push to on switch. Okay. Okay. Supervisory circuit, I think that's called supervisory circuit. Uh, Let me call it microcontroller supervisory circuit here. This one, supervisory circuit. Okay. It is called supervisory circuit for any microcontroller. Okay. Now coming to this part, there are two other interrupts which are dedicated for the timers. So there are two timers in 8051, timer 0 and timer 1. So these two timers can generate interrupt and inform the microcontroller that their task has been completed. Okay. And their vector, because every interrupt has got its own vector location also. Resets vector location, we can say 0 0. By default everything becomes 0. Vector location for timer 0 and timer 1 is 000b and 001bh. Okay. So whenever a timer 0 will generate an interrupt, it will go to 000b, and whenever timer 1 generates interrupt, it will go to 001b. Similarly, two externally dedicated hardware interrupts are there with pin number 12 and pin number 13, which are pin port 3.2 and 3.3. We have discussed that port 3 has got some important features like interrupts also. There are two interrupts which are available directly externally for the users. Okay, you can connect switch or any alarm or any sensors. So pin number 12 and pin number 13 are externally available hardware interrupts which are connected to port 3.2 and 3.3, and their vector location is 0003h and 0013h. These are the vector locations for external hardwares. Okay. External hardware interrupts. And then there is a single interrupt which is used for, this is not UU. Okay. This interrupt is for communication interrupt, communication related interrupt. Okay. So a serial communication related interrupts. So a single interrupt, one interrupt is dedicated for this communication also, and the location for that interrupt is 0023h, the vector location. Okay. So one interrupt is dedicated for both transmission and reception operations. So basically you have 5 interrupts. Okay. In the 8051, 2 interrupts for the user externally available. Okay. 2 interrupts for the timer and 1 interrupt bit for the communication. So basically we can say we can use by externally we can use 2 interrupts only. Rest 2 interrupts are timer and communication. And we have reset, we can consider it to be an interrupt, which makes it 6 interrupts in total. Okay. Done.